welcome to this explainer. Today, we're jumping right into what I honestly think is a truly epic narrative. We're going to bridge the unimaginable, violent vastness of astrophysics with the microscopic, exact precision of human nuclear engineering. We're tracing the life cycle of fissile material. It's a journey that starts in the pitch-black reaches of the early universe and ends right here on Earth, deep inside the reactor cores that light up our modern world and, the stockpiles that define global geopolitics. Okay, let's dive into this. Have you ever actually stopped to wonder how a dying star from billions of years ago could possibly power a city today? I mean, it sounds like pure science fiction, but it is literal, measurable science. The energy we extract from nuclear fuel here on Earth, it's actually ancient cosmic energy that got locked away during some of the most extreme events in the entire universe. So to understand our modern energy grid, we kind of have to start by looking up. The answer to that profound question lies in a mechanism known as the R process, or the rapid neutron capture process. Think of the R process as the ultimate cosmic forge. It needs an environment with an insanely high flux of neutrons. In just a fraction of a second, seed nuclei absorb these neutrons way faster than they can decay. This builds up these extremely heavy neutron-rich isotopes that eventually stabilize into the heaviest elements on the periodic table, things like thorium, plutonium, and the uranium we use today. In fact, roughly half of all the elements heavier than iron were born exactly this way. But where do you even find conditions extreme enough to drive the R process? We're talking about the most violent forces in nature here. For the longest time, the exact location was a mystery. But thanks to multi-messenger astronomy, which is where we combine light and gravitational wave data, we've now confirmed that binary neutron star mergers are prolific R process factories. As those incredibly dense stars spiral in and smash together, they eject a massive spray of heavy elements. Other theoretical cosmic forges include highly magnetic rotating core collapse supernovae and the swirling disks of material around black holes, which we call collapsers. To really wrap our heads around this, we need to zoom way, way out and look at the deep time of nuclear enrichment. Right after the Big Bang, 13.8 billion years ago, the universe only had light elements, mostly hydrogen and helium. But jump to around 12 to 13 billion years ago, and the very first generations of stars formed and died. We can actually see the chemical fingerprints of those early R process events preserved in ancient metal-poor halo stars that act like incredible cosmic fossils. Then, after hundreds of millions of years of celestial mechanics, binary neutron stars merged, seeding the universe with uranium. Fast forward to 2017, and human beings finally detected the exact moment one of these cosmic forges fired up with a kilonova. All right, bringing our journey back down to present-day Earth. Billions of years after those cosmic collisions, that exact star stuff is buried in our planet's crust as uranium ore. But, well, here is our major engineering problem. Natural uranium is overwhelmingly made of uranium-238, sitting at over 99%. The fissile isotope we actually need to power our reactors, uranium-235, makes up just a tiny 0.7% slice of the pie. It's incredibly rare, and that tiny percentage sets the stage for why human nuclear engineering is just so unbelievably difficult. We have to somehow isolate that tiny sliver. But before we can even worry about separating it, we actually have to get it out of the ground. Earthly extraction happens in a few careful steps. While some uranium is definitely still mined from conventional open pits, today over half of the world's uranium is extracted using an ingenious method called in situ leaching. Instead of digging a massive hole, we literally dissolve it underground. Oxygenated water or other solutions are circulated through the ore to dissolve the uranium, bringing it right up to the surface with minimal ground disturbance. Then it's milled, leached, and dried into a concentrated powder you've probably heard of, yellow cake. Now, yellow cake is really just the beginning. To separate the isotopes, we need the uranium to be a gas, not a solid powder. So chemists convert the uranium oxide into uranium hexafluoride, or UF6. This specific compound is chosen for a truly brilliant reason. It becomes a gas at relatively low temperatures, and fluorine only has one naturally occurring isotope. This is absolutely crucial because it means the fluorine atoms won't interfere with the delicate sorting process we're about to undertake. Any weight difference in the UF6 gas molecules will be strictly because of the uranium. Now, what's really interesting about this is where things get truly microscopic and honestly incredibly difficult. Remember, U-238 and U-235 are chemically identical. You literally cannot separate them with a chemical reaction. The only difference between them is 3 tiny, virtually weightless neutrons. U-238 has 146, U-235 has 143. That minuscule weight difference is the entire basis of the multi-billion-dollar global enrichment industry. Since we have to rely entirely on physics, enrichment has been an intense, ongoing technological race. We've evolved from gaseous diffusion, which meant forcing gas through microscopic barriers, a process that was massively energy-intensive and is now totally obsolete, to the current global standard, the gas centrifuge. This is where UF6 is spun at incredibly high speeds, so the slightly heavier U-238 gets pushed to the outside walls, and the lighter U-235 gathers right in the center. We're even looking at the future with laser separation, using finely tuned lasers to excite and separate specific isotopes.
Okay, so once we've successfully enriched that gas, increasing that rare U-235 concentration from 0.7% to between 3 and 5% for commercial power, we have to turn it back into something physical. The enriched gas is converted back into a solid uranium dioxide powder. That powder is pressed into small pellets and heated into a rock-hard ceramic. Finally, those little pellets are loaded by the thousands into long metal fuel rods, which are then bundled into the massive assemblies that go straight into the core of a pressurized water reactor.
And this brilliantly illustrates the sheer mind-blowing density of this cosmic power we've essentially bottled up. Just one single uranium fuel pellet, something literally no larger than a sugar cube, contains the equivalent energy of 1 full ton of coal. That is the incredible efficiency of tapping into the atomic nucleus. We are releasing energy that was forged in the explosive crash of neutron stars billions of years ago.
But here's where things take a serious turn. This exact same enrichment technology presents humanity with a dramatic fork in the road. The path we choose literally determines the outcome. If you stop enriching at around 3 to 5%, you get low-enriched uranium, or LEU. This is perfectly suited to power a commercial light water reactor and light up an entire city. But if you keep running those centrifuges, pushing the concentration past 20% and typically up to 90% or more, you create highly enriched uranium, or HEU. The exact same physics and machinery that create peaceful, low-carbon energy can also create weapons-grade material.
And uranium isn't the only material capable of a chain reaction. This brings us to the plutonium pathway. Plutonium is fascinating because it basically doesn't exist in nature. We actually breed it ourselves inside nuclear reactors. When that abundant, heavier uranium-238 absorbs the stray neutron, it can transform into plutonium-239, which is highly fissile. Since plutonium is a totally different element from uranium, we don't need centrifuges to separate it. We can use a chemical separation process known as Purex on the spent fuel. And because it's much more straightforward to chemically separate this than to use giant physical centrifuges, materials like MOX, or mixed oxide fuel, pose a serious proliferation risk that requires strict, rigorous safeguarding.
When these highly enriched materials are utilized for destructive purposes, the underlying physics dictate the weapon design. A gun-type weapon is relatively straightforward. 2 pieces of highly enriched uranium are rapidly forced together to achieve a critical mass. Plutonium, on the other hand, is prone to pre-detonation, so it requires an implosion-type weapon. This is where conventional explosives symmetrically compress a sphere of fissile material. It's also really important to note the risk of a dirty bomb. This doesn't create a nuclear blast at all, but rather uses normal explosives to scatter dangerous radioactive byproducts over an area, causing severe contamination. Beyond the explosive physics, we have to consider the profound biological stakes of interacting with these elements. For example, plutonium emits alpha particles. Outside the body, they're relatively harmless. They can't even penetrate a single sheet of paper. But if inhaled or ingested, they become intensely lethal to human tissue, linking plutonium to bone, liver, and lung cancers. Uranium, meanwhile, is less radioactive but acts as a highly toxic heavy metal poison, leading to kidney disease and autoimmune disorders. This is exactly why containment, proper disposal, and worker safety in the nuclear industry are absolutely paramount. Let's move to a wider view and see how this builds into a staggering global reality. 1,250 metric tons. As of 2024, that is the estimated global stockpile of highly enriched uranium. When you realize that it only takes a few kilograms to construct a devastating weapon, this number puts the sheer scale of human enrichment efforts and the immense security challenge we face into sharp, unmistakable perspective. To manage these massive stockpiles and prevent a global catastrophe, the international community relies on a really complex web of treaties and safeguards. The cornerstone here is the Non-Proliferation Treaty, designed to halt the spread of nuclear weapons.
Then you have the International Atomic Energy Agency, or IAEA, acting as the world's nuclear watchdog, conducting independent inspections to ensure materials aren't diverted from peaceful power generation to covert weapons programs. There's also a proposed Fissile material cutoff treaty aimed at banning the production of any new material for weapons, though negotiations on that have been stalled for years due to complex issues around verification and national security.
So the crucial point is this, and it's a sobering reality. The technology to enrich and separate these materials is out there. And as our sources highlight, the risk of nuclear terrorism or diversion by state actors will remain one of the most pressing security challenges of our time, for as long as these stockpiles exist. Securing this material isn't just a political goal, it is an absolute necessity for global survival. Which brings us right to our final question and the end of our cosmic journey. We have reached into the very mechanics of the universe, extracting the power of colliding neutron stars from the dirt beneath our feet. We can use it to light up the dark or to create unprecedented devastation. As we continue to harness the forces that forge galaxies, can humanity permanently master this delicate balance? It's a question that requires not just scientific brilliance, but lasting human wisdom. Thank you for joining me on this explainer, and keep questioning the universe around you.